very, very happy today to introduce Lauren, Alexandra, and Allison. I'll first introduce Dr. Lauren Wyatt, who is currently an environmental health scientist postdoc at APA's Center for Public Health and Environmental Assessment. She's actively working on projects related to air pollution and health outcomes in sensitive populations. And together with Alex and Allison today, they will be giving an overview on data visualization for environmental epidemiology that I know we are all very excited to hear about. So with that, Lauren, the floor is yours. Thank you very much.
Thanks for that introduction, Marianthi. So my colleagues, Alex and Alice and I are happy to present this workshop. We really think that data visualization is an important tool of effective science communication. And we're excited to create this workshop in materials that could be used as resources available for the further for the ISEE community. So Dr. Alexandra Larsen and Dr. Allison KRAJEWSKI, they're also wonderful friends and colleagues who I work with at within EPA's Center for Public Health and Environmental Assessment, and I'll let them introduce themselves further.
Yeah, so thanks, Lauren, and big thanks to ISEE for having us. I'm Alex Larsen, also working in the Office of Research and Development at the US EPA. I'm in the Chemical Pollutant Assessment Division. And I'll be starting us off, but do want to give Allison a second to introduce herself as well.
Thanks, Alex and Lauren. So I'm Allison KRAJEWSKI. I am an epidemiologist at EPA. I'm in the Center for Public Health and Environmental Assessments in the Health Effects Division. I mostly work on health assessments for the criteria air pollutants, and I've been doing a lot of my work is in air pollution and birth outcomes. I'll hand it back to you, Alex.
Thanks, Allison. Okay, so I'll get us started, and thanks again for all of you for taking the time to join us. Our format today, we're going to shoot for 3 50-minute sessions with 10-minute breaks in between. And as I mentioned, the three of us will kind of pass off those sessions to each other. And as we're going through, we'll be talking about ggplot and making figures with ggplot, and we'll also be switching back and forth between our slides and some code that we'll be working through in RStudio. And we'll be posting the code and the slides on GitHub, so those will be available after the presentation for you to kind of go through and work through the examples on your own if you wish. But as we're going through the talk, if you have any questions throughout, please feel free to pop those in the chat. We'll be monitoring that as we go along. And it's, you know, if you have questions during the talk, that's absolutely fine, but we'll also take some time at the end of each session to check in with the chat and answer questions as we're going. Okay, so our topics for today, we're going to start by going through what makes a good figure, and then move into the basics of creating those kinds of figures in R and using the ggplot package. And we'll talk about some data formatting, and that'll be our first session. And then we'll move into section 2 and talk about customizing the plot. So digging into how do we edit the scales, how do we choose colors and themes to make our plots stand out, and then also, you know, organizing them with things like facets. And then finally, our last session, we'll talk about pulling all of that together into making complex plots with maps. And we'll look at some examples from the literature as well. Okay, so let's get started with talking about what makes a good figure, what makes a plot effective. And this is, you know, a criterion that we will kind of use as a guide as we're going through each plot that we make in this workshop. So we'll kind of be coming back to these ideas. The first thing to point out is graph type. We want to make sure that this that the graph type that you choose is appropriate for your data and results. So if you're dealing with the time series, you're putting that on the x-axis so that your plot really facilitates explaining the data that you have. So that's something important to keep in mind. Another important thing that seems kind of self-evident, but it's really effective to, or really good to pay attention to make the plots effective, is that you correctly format scales. So making sure that you're including units on your plot can make a big difference in spelling out acronyms that allows your reader to look at a plot and quickly understand it, which brings us to our next point. Graphs are great when you can look at them and quickly understand the message that the author is trying to provide. So a good check for yourself is when you finish the plot, is it something that you can kind of quickly look at and get all of the pieces that you need, as opposed to having to dig through a caption or dig through another part of your paper, if this isn't a paper, or maybe a different part of your poster or presentation, if that's the format that you're working with. So making sure that message is clear enough that in just a couple of minutes, your reader can understand what you're trying to convey. And also using formatting to the best advantage of your plot. So formatting choices, they can help deliver the message, or they can obscure what you're trying to say. So making sure that if you're, using a color scheme, that you're picking something that really helps deliver your message, as opposed to just making the plot, look interesting, or something that might end up looking distracting instead. So, and the last point here is that, a good effective plot really helps to facilitate informed decision making. And that's really what we're trying to do when we're sitting down with our data and turning those into figures. We want our readers to be able to take that information and go about whatever decision making process that they are working on. So this is all about making sure your message is getting across and that it's actionable. Okay, so let's take a look at a couple of examples that hit these criteria. And this is a figure that's probably very familiar to all of us by now. This is the now sort of iconic Flatten the Curve graphic. And this is, of course, used by media outlets and healthcare systems earlier in the pandemic, to communicate the importance of implementing protective measures to help fight the spread of coronavirus. And this is, created in such a way that they wanted anybody to be able to look at it, even if you didn't have a background in healthcare, and to be able to understand the importance of different protective measures. And they did a good job. This graph became a widely used instrument for public health messaging surrounding COVID-19. We often heard that phrase, we need to flatten the curve. So let's kind of take a look at what makes it so effective. We have everything here is very clearly labeled. The axes, each of the curves, as well as the dotted line going across. So we just look at the graph and kind of immediately know what all of the pieces of it are functioning as. The use of color here is really nice. It's used to draw attention to these two different factors that the authors want you to make this comparison by. So, so using color to draw attention to that comparison that they want you to make between, what happens to the number of cases without and with the protective measures. So all of this together, the clear axes and labels, intentional use of color is allowing us to digest this figure pretty quickly, which is always the goal. Okay, so looking at one more example, this is pulled from the literature. It's not by any means a famous plot, but it's representative of something that we see very often in epi-journals. This is actually something from the American Journal of Epidemiology, and it's looking at age and sex-specific capture rates by the Rochester Epi Project compared to the US Census by age group. So again, kind of a representative figure that we might be creating. And this is nice because it has minimal graph elements, so it is pretty easy to read. And the axes are clearly labeled, and we also have units included. Let's see, I had a few animations on this, but I don't know if they're going through. There we go, great, okay. So we've got our units, and as I mentioned, all of the abbreviations are pretty are defined, which is always good. And we also have explanations for the line types. We do have to go into the caption for this, but that is an appropriate place. It's closer to the plot, explaining, why do we have solid lines? Why do we have dotted lines? What is that contributing to the story that we're trying to tell with this figure? So it's a simple graph, but it is effective and it is clear. So, today our goal is to become familiar with how to create these kinds of plots, how to create effective figures, and to use them specifically with ggplot2. So this is an open source R package that is tailored towards making scientific graphics. The GG in ggplot comes from a book or a text by Leland Wilkinson, The Grammar of Graphics, and his thought process is what this package is based on, and the Grammar of Graphics presents a theory that graphics can all be described, no matter what type of figure, as a compilation of basic components, and those components are kind of illustrated here on the right. And that if you have the ability to create any of these components, you can put together whatever type of graphic you need. So the ggplot package uses this grammar of graphics framework, where you're linking variables in a data set to a graphics component to build a figure from the ground up. And so while, this does, because of this, building from the ground up kind of mindset, it does require some practice to use, which is why we're all here today. But all in all, we're getting a lot of more flexibility and ability to customize figures that you might not get, in other softwares where you pick your plot and it's built in, and we're going from there. So those are the advantages of using ggplot, is the amount of flexibility and customization that you can use and employ in your figures. Okay, so let's get started with sort of the basics of making these ggplots. And I'm going to start a little bit with data formatting, so that the first step of making a figure, you have your data ready to go, and then we need to read it into R. So these are just a couple of functions that myself and my colleagues use most often when reading and writing data into R. R can read in several different formats: CSV files, Excel files, even text files. I would like to recommend using CSV. It's very user-friendly within R in particular. And so we've listed a couple of functions here to kind of get you started with reading in data into R. And the first one is read.csv, where you put in the name and location on your file system of the CSV file that you want to read in. There's other options, like whether or not your file has headers, and you save that to a variable, and then you can start editing that data set within R. And then write.csv is pretty much follows the same format. You give it the R data frame that you want to write out, and the name and location of where you want it to be saved on your computer. And it also includes features like whether there's headers and those kinds of things. So instead of talking with you about code, I'm going to actually switch over to RStudio, and let's see. Switch over to RStudio and go through some code together. Okay, let's see. There we go. And as I mentioned earlier, we will be going through this kind of format where we're working in the slides and then working within RStudio to kind of go through examples. So I'm going to increase the font here just so that it's a little bit easier to read. Okay. So for those of you who are maybe new to R Studio, we probably won't spend too much time going into the mechanics here, but if you have any questions about that, please feel free to pop those into the chat. So this is an R Markdown file we'll be working from, and again, we'll be posting this on GitHub. And let me just get us started by loading the different libraries that we'll be needing today. So as you can see, I'm running code over here in the left panel, and then my console is over on the right, and it's giving me feedback on what it's doing. Okay. All right, reading and writing data sets into R. So here are the two functions that I was talking about over in the slide, so read.csv and write.csv. And I mentioned that, it's as simple as putting in your file here, and you can see some examples of that down below. So these are some data sets that I might have saved on a computer. I'm putting that into the function, read.csv, and saving it to a variable name. If you have, any questions about, what other types of arguments you can add to this function, something you can always do with R is use the question mark feature. I'm going to pull up what that does. So if I run that line of code, question mark, and then the function read.csv, the help page pops up. And this tells us everything we need to know about read.csv and all the arguments that it can take. So read and write.csv are just one of several functions that you could use to pull data into R. And in the Markdown file here, we have those listed out in case you're interested. If you're familiar with the tidyr package, this is their version. This read.delim is a very flexible type of reader. It allows any other delimiters besides comments, and we also have fread down here. This is really good for large data sets, so just pointing it out. Okay, let's see. I'm going to go back to PowerPoint. Okay, so reading and writing data into R. Talked a little bit about those functions, and looked at some examples. I mentioned the tidyr package for data manipulation, and I wanted to touch on, data manipulation because, again, when you're starting to write these, write your figures within ggplot, we do need to usually do some data cleaning before getting started. So we're going to talk a bit about that today. So tidyr is a package that we'll be working with. It's a library with an R for data cleaning, and it includes very intuitive functions for doing all kinds of data manipulation techniques, like subsetting your data, pivoting, and we'll go into a couple of those. One thing I wanted to point out is that both ggplot2 and tidyr use the pipe operator. So this is something where instead of directly putting your object or data set that you're interested in directly into a function, you pipe the object into a function that has the specific arguments. And that might be a little opaque to understand on the slide here, but we'll go through some examples later on. It really allows you to streamline your code. It makes it easy to read. And again, this operator is something that's used in ggplot2. So working with it within tidyr is, kind of complements that technique. So let's pop over to our studio again and go through an example now of using that pipe operator. Okay, so we're back in R and working with the pipe operator here. So what I'm going to do is I'm going to get some sample data together. So this is just a sample from a random sample from a normal distribution with 1,000 samples in it. And I'm going to compute the mean of that using sort of your standard setup where you have a function of a mean and you're putting your object or data set into that function. And here is the same process if you're using Python. So you have the data set and you're piping it into the function. And as you can see, we get the exact same thing. So that's a very simple example. Here's one that's a little more relevant to us, since we're talking about plots today, making a bar plot. So this is the iris data set. This is a built-in data set to R. So we don't have to bring any data in. We just call the name and R knows what we want. We're looking at the first 6 rows of the data set here. And say we wanted to create a bar plot where we're comparing the average of each of these columns or variables here. But we just want to look at one of the species. There's several species in this data set, but we just want to look at one. So here's the line of code that does that. And you know, we get what we're looking for. But I would argue that this is a little bit tricky to get through. There's a lot going on. And we can do it in a little bit of a clearer way. And that's with using the pipe operator here. So here, you have your data set, you're piping it into your first function. That first function is to filter out everything except for that Setosa species in the data set. And then once we do that, we want to select these are the variables that we column names we want to look at, and we take their column means. And then we want to make a bar plot. So we have this very logical order of operations here that we can see very clearly when we're using the pipe operator, and we get the exact same plot. Okay, so that's the pipe operator. Moving back to our slides. We'll go on to the next topic in data manipulation, which is long, looking at long versus wide data. As I mentioned, you know, there's lots of different data manipulation things that you might want to do to your data before you create your plot, and converting between long and wide format is something that, you know, we have to do pretty often. So we wanted to talk about how to do that today. So just to refresh, long data is typically more narrow or stacked. You have one column containing values and another one containing the description. And when you're going to long from wide, you're lengthening the data. You're increasing the number of rows. That's where it gets its name there. And vice versa with wide data, each variable in the data has its own column. And going from wide to long shortens the data. And this is the typical format that we use when making ggplots. So we'll work through an example now of going from a long format into a wide. All right, back to our studio. Okay. So again, this is a very, you know, common type of data manipulation that comes up when building plots with ggplot, because it likes having, you know, the variable name in one column and the value in the other. So we're going to do this with the same iris data set. And again, we're looking at the first 6 rows up here. And what we want to accomplish here is to get the data. We want to look at the flower parts here. So the sepal length and width and petal length and width. We want those in one column, and we want these measurements all in another column instead of having them spread out. So I'm sorry, I misspoke. We're going to be going from from wide to long. That made them a little confusing. Going from wide to long with this data set, not long to wide. Okay, so we'll save this as a variable iris_long, since we're lengthening the data set. Start with the data iris, and we're piping it into a function pivot longer. This is another one of the tidyr functions that is one of the easiest to use when it comes to doing pivoting from long to wide, and vice versa. So here we want to pull out these columns, the first 4 columns here, and we want to create a new variable, a new column called part for the flower part. And we want to create another variable called measurement, where we'll see the rest of the data. So we'll run this, and we'll take a look at how that looks. So now we have lengthened the data from having wide format with these separate variables, all separate from columns, and now they're all in one column, and their measurements are in another. Okay, so that is our example from going from long to wide. And if we wanted to go from wide, again, just a kind of dummy variable here, saying that this is just .csv as our data file that we're bringing in. So next we have a couple of lines that control the geometry of the plot, or the plot type. And then, so here, the geom is the geometry again, the plot type. We're controlling what points to put on the graph. So we have, what points go on the x-axis and the y-axis. We can control the shape of the plot here and the type of the line type, which is this LTY. And then we can also add a horizontal line, this next line of code with y = 0. So that's again some pseudocode for what might be behind the figure on the left. The next chunk of code controls the theme. So we have a very minimal theme going on. There's nothing really in the background, it's just black and white. And that's what this theme sets. It's theme_BW, which is just black and white. And we'll be getting in later in the talk to how, what other types of backgrounds are available and the different styles that you can use built in with ggplot. The next chunks of code control the labels and the axes. So you can see here that on the y-axis, we're limited between -30 and 30. That would be controlled with a line of code like this. There actually isn't a title for this plot. That's another thing that we can turn on and off. And we can also, there's functions for adding your X and Y labels. And other things that, again, we'll be getting into a little bit more detail later on. And finally, we have skills and legends, which control the aesthetics of the plot. So since we have lines, we can control what those lines look like with the scale line manual function, and control whether or not there's a legend. So as you can see with this figure, there was not a legend. So we're saying that guide is turned off. So again, this is kind of a very quick overview of some of the functions. We'll be diving into all of these later on. But right now, I'm going to focus on the geometries and how to create just basic ggplots before we get into more customizing. So again, we start with a call to create a ggplot. Starts with that call to ggplot, and then we iteratively add the graphic components as layers. And in each component, we specify the data set that we're going to be working with. In most cases, it's one data set for one figure, but sometimes you may have a couple of different data sets to pull in. So we specify that with each component. We also, in each component, map the aesthetics of the plot to the data. So that's a linking variable from the data to the graphic components. this note here is actually important. We do need the data to be set as a data frame type, not numeric or matrix. So it's a little bit technical, but a good thing to keep in mind as you're creating the figures. Okay, so this is the sort of framework for the code to create a different plot type. It starts with geom underscore, and then whatever plot type you're interested in, whether it's a bar plot or a histogram or scatter plot. We have some examples here. This link is to a really comprehensive reference page on ggplot2 geometries and different plot types that you can make. It not only lists the different types, but also gives you some examples and how to use each function. And all of these geom functions, they control the points and the lines, bars if you're doing bar graphs, or polygons if you're doing maps that go into making each type of plot. So let's go to an example and make a simple plot to kind of get started with the idea of working with geometries. Okay, so I'm going to work with another built-in data set to do this example. This is called Faithful, and it's a data set based off of old Faithful, looking at eruptions and waiting time. So if we wanted to make a plot with waiting time on the x-axis and eruptions on the y-axis, this would get us there. So so here we go. This is the figure that we're wanting to make. We have our ggplot starting us off, and I've fed in the data here, and then also mapped the variables to the different aesthetic factors. So in our case, we're just mapping waiting time to the x-axis and eruptions to the y-axis. So getting that all set up in our first function here when we're initializing the ggplot, and then I'm piping that or adding on the geom point layer to the code so that it knows that we're wanting a scatter plot. So a couple of things to point out with the syntax here. We could also create the same, could create the same plot, putting the data and the mapping details into geom point. So here we're sort of initializing, and if we wanted to use one data set for the entire chunk of code, we could put our data up here. And for each layer that we're adding on, we anticipated X being waiting, Y being eruptions from that data set, then it makes sense to put it up here kind of globally with ggplot at the top. But if we wanted to change, we can also put these options within each layer. And give that a run so you can see, get the exact same figure, whether or not your data is here and local to this geometry, or whether it's global and sort of automatically applying to all the geometries that are there. Okay, so just kind of honing in that mapping is this function that is connecting the data to your plot. If the figure doesn't have, if you just give it faithful and ask it to run, it will say, well, what do you want me to do with this data set? But when we add in mapping, that is what allows ggplot to talk to your data. So that's obviously pretty key to creating the plots. If we wanted to change the aesthetics of the plot, mapping is where that happens. So here we'll do a quick example of that. Say we wanted to change the color of a plot. This is a pretty basic aesthetic that we might want to change. We could link it, we could make the whole, apply the color to the whole plot. We'll try to apply it to the data. I'll show you what I mean by that. So let's say we wanted to create this basic scatter plot and color the points blue, just maybe because because we can, because we want the plot to look a little more interesting. So we think, well, maybe if it has more color, it'll stand out. So I'm applying color here outside. It's its own argument in the geom point layer. Saying I want that color to be blue, and there we go. All of our points are blue. Looks okay. As we were talking about earlier, it's good when color actually helps tell the story. So this doesn't really, it's not too different from having the points in black. They're all kind of the same. But say we wanted to draw attention to the fact that there's a cluster of points over here and a cluster of points over there. And it looks like that cluster is happening, above, 3 eruptions and below 3 eruptions. And we wanted to color those points differently based off of those 2 values. What we could do is come into the mapping function where, again, we're linking to the variables in the data set and say that we want color to depend on one of those variables. We want it to depend on eruptions, and specifically when eruptions are greater than 3. So if we run that, now we get this nice split. We're telling a little bit more of a story that, there's a kind of a clustering going on. We can sort of just see from looking at the plot between waiting times when eruptions are greater than 3 and less than 3, and our colors have been plugged in there for us from ggplot. Okay, so that's all of an example about creating a basic plot and going through putting in your data, putting in your mapping, and setting your aesthetics. Let's look at a couple of different types of geometry. So we were looking earlier at just scatter plots, but say we wanted to look, we could make a histogram of the eruptions, and that just involves changing this from point to histogram. So we have the same setup, but we're changing the geometry from point to histogram, and we get a nice histogram figure here. So we can, manipulate different things within histogram, and that's, what you can change with histogram is going to be different from the scatter plot. One thing that I often do when I'm working with histograms is changing the bin width. And here R is telling me that the default is 30 and actually suggesting that we pick a different one. So that's something we can do. And this isn't going to depend on any data, any of the variables. So we put that outside of the mapping function and change the bin width and get a little bit higher resolution on our figure. And that's pretty good. Another type of plot that we could make is a box plot. So if we go back to our, we'll do that by going back to our iris data that we were looking at earlier. So say we wanted to just look again at that Setosa type, we would pipe iris into filtering and just pull out Setosa. And then I'm going to take out, so if we do this, we get a data set that's just for Setosa, but if you go click through, see the species column has Setosa repeated all the way through. So we don't need that column in the data set anymore. It's not giving us any more information. So I'm going to take that out here with that select function and take a look at the first 6 rows, and that's looking pretty good. We just have the data that's useful. So for this box plot, we want to have parts of the flower on the x-axis and the measurements on the y-axis. And if we look at this data set, there's no information on the parts or the column names, and the measurements are all within the data. What ggplot needs is to have an actual variable name that's parts and one that's measurements to be able to kind of pull that information out and put it into a ggplot. So since we don't have that here, we are going to have to pivot the data into long format as we did earlier in order to get this parts and measurements set up. So let's run that. This is the same line of code from earlier. And now we can we can see why having this pivot from wide to long for that Satoshi data, what we can do in terms of making that into a nice figure. Okay. So we want to make this box plot. We're starting on ggplot, adding on a box plot geometry. And within that, we're going to set our data set to the Satoshi that's lengthened, Satoshi long, and we want X to be part and Y to be measurement. We also want to give this a title. We want to highlight the fact that we're just looking at the Satoshi species from the data set. And get a nice box plot where we can compare the different measurements for this one particular flower type. Okay, so those are, we've just worked through a couple of examples for making basic ggplots and changing geometries around, and where to put your data in and into the function, and also where to how mapping works in terms of connecting your data to the aesthetics of the plot. Last thing to talk about now, since we have a nice figure, is how to save. This is sort of the last part of basic ggplotting. Is now that you have your figure ready to include it in a presentation, this is how we save that figure. We use a function called ggsave, which you call after making the plot, and it defaults to saving the very last plot you created. So if you created 10 different plots and you put ggsave at the bottom, it'll just save just the last one. So be sure that when you do that, you either add ggsave after each figure, or you put all your figures into one figure, which is what this next group of functions, these are all options for doing that. Create a range is something that would allow you to create, a multi-plotted figure. Same with multi-plot and gg arrange. So we'll go to one last example for this, where I'll kind of walk through saving your figures. And I'm going to be focusing on ggsave. So say we wanted to save our that faithful plot. We made it blue. Let's go back up. And so if we ran that line of code right now, it would save our box plot, because that was the last one run. And we go back, and it's not a blue plot. Here it is. Okay. So we wanted to save this. Okay. Notice that I've entered in the file name, so this is how I want it to show on my directory, and I've also specified the width that I want and height. So you can manipulate here when you're writing out your image, the width and height. You can also specify the resolution of the image. This is something that papers sometimes ask for, is changing the DPI. So you can set that in here. And we can also, I have it going out as a PNG, which you could save with as a JPEG or a TIFF, whatever format that you're looking for at the time. So I've run that code, and if I go over to files, you can now see that image is saved. And I don't know if that photo is popping up for you guys, but it saves it right into the directory that you're working in with R. So that's the sort of simplest way to output plots. If you have multiple plots, and instead of wanting to save them one by one, you wanted to create a panel, I'll show you now how to use grid arrange to do that. So say we have two plots. This is our Old Faithful plot where we're using two different colors based off of erection, and this is our blue one. I'm going to save these ggplots as variables, so P1 and P2 for plot 1 and plot 2. So I won't print the plots out, but it does know that P1 and P2 are the plot. And then using grid range, I can put these two in and tell R that I want 2 columns. So I want these to be side by side. So if we run that, preview, now we have our 2 plots side by side. So say maybe we're, trying to remember why we did, these 2 colors as opposed to 1 color. And we save both, and we have this 2 colors gives us a little bit more information than the 1 color. So we have that all saved in 1 figure, and I'm going to call that P3. And so we can put that directly into ggSave. And again, the way ggSave works, if we just ran it, it would save the last plot that we made, which is the side-by-side plot that we want. But you can also name your plot and feed it directly into ggSave. And that's another way that you can kind of keep track of what you're writing out. So we've set the file name, also doing PNG, set the width, set the height, and have it at a pretty high resolution. And if we write that out, it pops up in our files. So that is how to use ggSave. Again, there's a couple of other functions, but this is sort of the go-to to write out your files once you've created your wonderful plots for your paper or your presentation, or just to keep track of your research. So that is it for section number 1. We've sort of gotten to the end of the basics of creating a ggplot and the basic data manipulation techniques that you might need, and again, that overview of what makes an effective plot, which is something that will kind of come up throughout the rest of the talk. So I am going to pause and see if anybody has any questions, or if not, we'll go ahead and take our first 10-minute break. So I'm not seeing any questions in the chat right now. So let's go ahead and do our break. If you have questions during the 10 minutes, feel free to pop those in there. Otherwise, we'll go ahead and break and see you all back at 1.
Hi, everyone. Welcome back from the break. So we're going to move on to section 2. If you have any questions, please pop them into the chat. So I am just going to jump right in. So first up, we're going to be talking about scales, and thankfully for Alex's presentation, the first part of the talk, she was able to talk a little bit about using scales. But I'm going to go into a little bit of explanation more of what they are and how you can modify them in ggplot. So the scales control the mapping from the data to the aesthetics, and then they provide everything that you want to manipulate in your plot: the axes, the legends, the colors. And you can do this. You can generate a lot of plots without knowing how to manipulate the scales, and they will use the default, and that's perfectly fine. But to have a better representation of your data and what you're trying to convey in your figure, using scales is more appropriate and can help you to give much more control of what you present, how it looks. And from this, you can change the position and the X and Y scales. You can do colors, you can do manual scales. There's different types. So for each space within the graph itself. So to modify the scales, first thing is that they're made up of 3 pieces. So it's usually this, it always starts with scale, and then the name of the aesthetic, which is either going to be your color, your shape, or your X or Y axis, and then the name of the scale. So it could be, in these examples here, are just 2 brief ones of scale _ X continuous or scale color discrete. And there's a bunch of different ways that you can manipulate the scale, or a lot of different scales you can manipulate. These are just a couple of examples. So the labels is another piece of the scales in which you can create more specific labels to your graph. So the X and Y axis labels will always default to the variable name. And personally, I don't always have the best variable names. I know what they are, they're usually shortened, but that's always not the best representation that you want on your graph. So to modify those scales, to change the label, there's a couple ways you can do it. And these are just the scale X continuous, and then you can modify it within that command, or you can do it as a Y lab, X lab, things like that. The labels can also be super helpful with mathematical expressions, superscript and subscript, which is something that's pretty common and for like units of measurements as well. And it's really nice to have that flexibility to add that level of detail to your plot. Another big part of what you can modify within the scales is breaks. So these are the controls which the values appear as the tick marks on your axes, and are also helpful for the keys and the legends. So if you set your label arguments, then you can set your break arguments, and it's just as easy as that. If the data changes, the breaks will no longer align with the label. So you have to be careful about how you're setting your labels and your breaks within your scale. And then the breaks can be used for the continuous or categorical scales. You could do a categorical scale can use a named label vector. So it could be like scale _y discrete labels, and then you can call them alpha and beta. You can also use the breaks to suppress, you can also suppress breaks on axes and grid lines for the labels, and by setting them to null. So these are just a couple of different ways that you can manipulate within scales that can be more specific for your graph and how to make it more functional for you. So the last thing I'll talk about before I go to some code is the legends. So legends are helpful in displaying results, and they can also be modified easily as modifiable as the breaks and the labels. And then, but where you place your legend and how it appears in your figure is something you want to be you kind of want to think about too, because sometimes how you've represented your data, all that labeling goes into your legend. So we have to be careful about how we want to display that. So I am going to go to my RStudio. Hopefully it comes up. Okay. So as I mentioned, that everything inside the AES, as Alex mentioned, will have scales. So if you just wanted to create a basic scatter plot without specifying scales, that's perfectly doable, and it'll go to the default. Now, as I mentioned before, your variable name will be used as your label for your Y and X axes. And this is, I created this label name using ozone data by year, so we can see it's an ozone _ppm. So if I wanted to make that more specific and not have just like, if I wanted to specify what that unit was, you can simply change the label. So that is by adding in, so my scale X continuous, and then I'm going to call this year, which was the default used in this graph above. But the axis is now going to have, I'm going to call it ozone concentrations and change it from just ozone _ppm. So it's just adding a couple lines of code, which comes out to be this. So it's a little bit more detailed of your labels, where it's not just straight up my variable name. You're actually calling it the ozone concentrations, and then it's plotted by year. So this is just another example of how to add labels using XLab and YLab. Up here we use X_scale, scale X continuous and scale Y continuous. And this will just generate the same graph, just a different way to do it. You know, there's a lot of things in R that you can do in multiple ways. So whatever you're most comfortable in, and these are just two common ways. So as I mentioned before, the labels can be helpful in being created with the mathematical expressions. So this one, I'm adding in my label for year, and then for on my x-axis, and then for my y, I'm going to say that I want my ozone concentrations, I want to add in this mathematical expression for it. So, and it'll just superscript the ppm. Now, I mean, this is just an example and not necessarily something you would do with your units, but just an example of just how adding in this quote and then adding in this caret for the ppm allows you to put in something for like mathematical equations for superscript. So this one, I'm also going to show you how to do superscripts and subscripts. As we know, we use a lot of chemical symbols and abbreviations in a lot of environmental and a lot of environmental plotting. So this one, I'm going to use NO2 as my example. So here I use my XLab and my YLabs instead of the scale Y and X continuous. So again, it's just the year. But now by putting in this YLab expression with this notation here of putting the brackets around the 2 within here, you can see that I have subscripted. And that's just another point, like we, superscript here, we can subscript here. These are just easy ways to put in things for mathematical equations and that are more relevant and more detailed for your specific ggplot. So another point I had made was the breaks. So we want to create these specific points, right? So I'm adding in, again, it's just my scale X continuous. I now have my label, but now I'm setting my breaks. I want my breaks to be on my X scale, which is my year. I want that to be between the year 2000 and the year 2020. And then I am not changing the Y on this one. This is just creating the same default, similar to what we saw before. But now I'm going to specify the breaks for the X and the Y. And as you can see here, these are the predetermined, these are the defaults. So I'm going to run this code, and I've specified my limit here that I want my minimum to be 2000, my maximum to be 2020. I want my breaks at these specified points instead of what was predetermined for me in my defaults. And we get this plot. And I've also added in something for color. As Alex had mentioned earlier, color is a simple addition to the plots. And I'll get into color a little bit more in the next section too. But as you can see here, it's similar plot to what we had before. We have a legend added now. We have gradient scaling on color and I set my limits from 2000 to 2020 on my X, and I set them at 0.06 and 0.09 on my Y. So you can also, I'm going to use a different example with hypertension data. So I'm just going to create this base plot here. So I have the top 5 states in which total hypertension prevalence is the highest. I've added in, again, my label, which is for my X, which was state. I've added in my label for my Y, which was total hypertension prevalence in percents. And I have defaults for color, and I have defaults in my set for the legends for the specifying male and female. So with the addition of breaks and labels, I am going to create a more specific, a more refined graph in which I'm going to be looking at the x-axis is a little busy with the full state name. So if I wanted to abbreviate those within my label, within the label statement here, I would put in that I want Alabama to equal AL, District Columbia, DC, and so forth. And then that's the only thing I'll change in this plot. And then there you go. I have the abbreviations down here. So, I mean, setting up things for the defaults can be okay, but you know, this just gives you a little bit of functionality or a little bit more control over how the aesthetics look within a plot. And it helps to clean up your x-axis a little bit. And it's just adding in a little bit of extra code here. So the next thing that I'm going to talk about is changing the position of the legend. So the default position is always to the right of the figure. So I'm going to go back to my ozone plot. So I'm plotting ozone for, you know, across the time, which we had looked at before, of from 2000 to 2020. I have my concentrations for ozone on my Y, and again, the legend appears on the right. So if I want to specify a different placement for that, I can just add in this line of code here, which is theme, and then within it, legend.position equals right, which will show you the same exact thing as in the default. So we now have control here of where it, we now controlled where that position was by just simply adding in this. So, but if I wanted to change that, let's say I don't like that it's scrunched, or I just prefer it at the bottom, all you have to do within the theme for the legend.position is change it to say bottom. So now we have it down below, and it doesn't change anything from the way it looked up here. It's just in a different placement. You can also modify the legend so it'll be in a single row, as I'm going to go back to this hypertension example before. We saw states across the X and across the Y. We saw total hypertension prevalence, but we had two groups. We had males and females. Again, I'm still going to be using my labels that I created for the, more specifically for the state abbreviations. And then again, I'm just putting in my legend placement. I want it at the bottom, and I want it in run row. So I'm just going to run this. And then we see now we move the legend from the right down to the bottom. And it, you know, depending on how you, what kind of data you have, you know, you may want to leave the default of putting the legend at the right. You might want it at the bottom. But when you, this is super helpful for legend placements when you're thinking about if you're going to facet things together or grid them together, as Alex mentioned too. So, and that's what brings me to my next point, is that you may not want a legend at all on this particular, on a particular graph, because you may be faceting them together. So then that means that every, let's say you have data for top 5 states, top 10 states, but you want to facet those together at the end, which means just grouping everything together. To make it more streamlined and easier to read, you may not want legends on all of those figures when you put them together. So I just changed my legend position to equal to none. And this will take the legend away. It doesn't take away from, it doesn't take anything away from the graph itself, but it does take away the legend. So it could be potentially helpful if you wanted to, you know, facet together ozone concentrations, lead concentrations, and PM concentrations, and later on. So I am going to go back to my PowerPoint.
Hey, Allison, we've had a couple of questions pop up in the chat. So I wanted to see if you wanted to take a quick break. We have one from Trent asking if it's whether or not it's preferred to label a variable outside of the ggplot or just label things in the graph directly. He's asking specifically about the label function, but I think it's a good question generally, about when it's advantageous to label your variables outside of ggplot versus inside.
Yeah, I don't know. I feel like sometimes as a personal preference, I guess, I mean, I don't, Alex, Lauren, do you have input? I mean, I try to pre-label them before I bring them in, but that doesn't always work. I feel like sometimes with the labels within ggplot, though, I have a little bit more control if it's not exactly what I thought it was going to look like, if that makes sense, when I started making my plot.
Yeah, I mean, I think, the example that you've been walking through where when you're in a situation where you have to change things like, say you're reporting something in micrograms per meter cubed, and, it would take a lot of work to create that label within R as opposed to creating it within ggplot. So that's definitely a case where you'd want to do inside.
Yeah, I think, I mean, I've just seen some plots before too where people forget to change the labels before bringing it into R to format for your plot specifically. And if you do that, it's not, an issue. You can still change things once you bring it in, or to create your figure. So, it just gives you a little bit more flexibility in that sense. You said there was another question, Alex? I'm sorry.
I think that was the main one. Thanks. We had another comment from Hannah, who says that she usually applies variable labels to avoid needing to copy and paste if you're creating multiple graphs with the same variable. So I do think that's a really good that's a really good point, Hannah. Thanks for chiming in. So okay, thanks, Allison.
Yeah. Okay. So I want to go on to colors. And again, if you have questions, please just drop them into the chat. Colors is a really interesting topic to cover. I feel like sometimes people can go overboard with trying to make things look really nice, and then sometimes the figure is just so overwhelming because there is so many colors. So just a couple of things to keep in mind. So for colors on the continuous scale, you have a couple of options for how to pre-designate. There's some options for pre-designating your colors, but you can also create them, which I'll get into as well. So you have these scale options here, which is scale color for your gradient or your distiller, and then you also have a fill. So for note, usually when you use things on a continuous scale, you like to keep within the same color scheme or use a gradient for that. Whereas for discrete values, you can keep them as, keep the color scheme colorblind friendly at least to represent different colors. And you can do, there's some preloaded packages in R as well, and you can use the color brewers to create colors. There's a bunch of websites online to help you as a resource for deciding colors, especially if you need something that's colorblind friendly. There's also different ways to do, there's some ways, some journals prefer that you provide everything as grayscale. So there's options for that, like preset grayscales, and then you can manually change your colors. One thing is that these are the color brewer. These are all preset color palettes. They have different sequential patterns. These qualitative and divergent colors as well. And then there's another package of Veritas. So, you know, these are just scales of gradients for colors. And there's a lot of different options for colors. And you can also create your own color palettes, which you use the breaks to do, which I just talked about before, which, you know, you can use them to create your limits or where you want your data to have breaks at, but you can also use it to create a color palette. So the pre-existing color palettes, which I just talked about, was in the scale _ color _ Brewer, but you can use hex codes to create your value, to create your own color palette, but you'll have to first create your values and then you have to specify with manual. I am going to go back to my R, and I'm going to keep with my two examples, my hypertension data and my ozone. So just some general considerations. You usually don't want to use red and green together depending on your data. Red and green together, usually red means bad, green means good. And I feel like sometimes you see things and that's not always how you want to represent your data, because you don't always want to say red is bad, you know, per se, but it's not, it can be alarming to some people when they see red on a graph. Rainbow gradients can also be very hard on the eyes, and they're not always colorblind friendly, so be careful about that. So I'm going to go back to my hypertension example. So this was my default. We used, you know, we didn't specify anything. We just said we wanted to create a plot. The color we want by sex, which we do have here. So it's at least knows that specification to use two different colors. However, if I want to use color Brewer, I can just add that in here, so I specify in my aesthetic that I want to have two different colors because I have two different variables, categorizations, and I just add in this scale _ color Brewer here. This, and then I get this color, and it can't really see females on this graph very well. So what I can do is change this pre-existing palette. So I just let the color Brewer pick one for me. It was a default. In this next example, I can use the color Brewer with a pre-existing palette, which I had shown on a previous slide, and I'm doing that by saying my palette is equal, I want greens. And we have them plotted in greens instead of blues. Another way you can do this is to say that, you know, this just isn't working out. These two colors are too close together. They're not showing up well. So instead of saying that I want just a single color palette, I can say that I want this this other color palette where it's signaling to make two different color choices of, you know, females are green, males are this purple color. So you're not following that same, it's one variable with two categories, but you can display it in a couple different ways. The other thing you can do is reverse the colors. So let's just say I want males to be green in this example. So I do that simply by adding the direction is equal to -1 to my palette and within my scale color Brewer statement. So it is the same plot as just reversing my colors now. You can also do what I talked about. We can do things that are outside the pre-existing color palettes. So I can look up color names or look up hex codes. So first off, I'm going to need to set my color palette. So in this instance, I want males to be black, females to be this deep pink color. So I'm going to just run this, and I set that as my figure color. And then within my color command here, I'm saying that I'm going to manually set this because I have now created my own color palette, and I want the values of that palette to be the figure color, and I want the breaks to be for the males and females because we have the two variables. So I'm just going to run this real quick. And then we can see that I have now manually created my own color palette, and I have changed it so that it recognizes it as males as a black color and females as a pink color. And as mentioned too, you can create your own hex codes by looking them up online. You can just Google them and say, you know, you want hex codes for this. And they easily come up. So again, I'm just resetting my figure colors for black and this pink color. I've now replacing in my scale color manual statement that I'm going to use the newly created color palette, and again, my breaks to determine which is which. So same figure, just a different way to do it. You can use it either using these color names up here, or you can use it with the hex codes. So you can also create high resolution figures. Like if I wanted to use this figure in a manuscript, you can create them through high resolutions. So you can do it by specifying a DPI, because some journals will specify that they want that. And so within ggSave, I'm telling it where to save it. I'm calling this my hypertension JPEG, and I want it at DPI 360. You can save it as a PDF as well. There's different specifications you can use in ggSave. Depending on what the journal is requiring you to use. And you can also pre-specify a width and a height and units within inches to save it. These are just different options you can do once you have created the plot you would like to use for your publication or for a poster or whatever you may need your figure for. So these are just easy ways to do high resolution figures, because the lowest DPI usually for high res is 360. So I think if there's no other questions, I will hand it over to Lauren, who will talk about themes.
Yeah, thanks, Allison. I'll start sharing my PowerPoint screen. Okay, so in the theme section, I plan on covering what a theme is and how it can help improve your figures, go over some pre-existing themes that are useful for getting started, discuss some of the naming convention that's used for further customization, and also run through a couple of examples with some of the common ways to improve a figure. So a theme allows you to customize the non-data parts of your plot. And this can include the titles, the labels, fonts, background grid lines, and it can take your figure from sort of an initial data exploration to being more polished and focused with a message. And it's just as important as the actual data to focus your message to an audience. So a good use of theme is to focus the attention to the data by specifically choosing what emphasis or what information should have emphasis. So removing graph details that are less important through decluttering. So in this top example, your eye can bounce around from all the lines, from the bounding box to grid lines, and that can create unnecessary effort for a reader. So by removing those, it's easier to focus straight away on the data points themselves. And for maps, I prefer removing all background elements because really, unless in like specific cases where specific latitude and longitude are important to the presentation, a lot of times they're just extraneous information. So ggplot comes with a number of pre-existing themes, which can allow you to quickly transform a figure. And the gray theme here in the top left corner is the default. And the customized themes really differ mainly by the background, grid line, color, and intensity. And shown together, we can kind of look through them. Between the gray and the black and white themes, removing that background color really allows more focus to be on the actual data points in those top tiers between theme gray and theme underscore BW. Lightening the grid lines or removing them, sort of moving between light, minimal, or classic, also places more emphasis on the data. And so your choice will really depend on what's important to the message that you want to create. And the pre-existing themes are a great place to start. And you can use the theme argument to easily make additional changes. So the main components within theme are line, text, and rectangle elements. And line elements include axes, grid lines, borders. Text includes things like title, the axis, legend text, and rectangles can be backgrounds of either legends or also the main plot background. And there's a number of functions that can refer to the different components that can allow you to change the color, size, line type, angle, and fill of a lot of these different components. And we'll get into that in this next slide. The naming convention, so changes can be made generally. So in this first example, we're using the theme call and calling axis.text. So we're planning on changing axis text, but it's being general. So it will change both X and Y axes. We're specifically in element text specifying size. So the size that we set will change both X and Y. But we can also be more specific about this in terms of adding .x in that bottom one, where now only the text size for the x-axis will be adjusted. So the example we'll walk through will really show the utility of using theme. It will use a time series plot of daily ozone measurements in 2 cities. And the source for this data, air pollution data, comes from the MLbench package. And their temperature data was used to create, in quotes, another new city. So improvements that we're planning on going through include adjusting grid lines, text size, rotating axis labels, and adjusting some space between panels, and then where to place your legend. I'll switch to RStudio. In this first plot, after loading the data, we'll run this first chunk and we'll see that we have our first base plot that uses the generic gray background, and using facets, which I know we'll get into later, just separates so that we can see the 2 cities side by side. So our first adjustment might be to remove this background, and we can do so by adding additional argument to this base plot by using theme BW, which we've also seen before, which now allows those green and orange dots to be more prominent. But an additional adjustment we might want to make, since there are a number of grid lines, is to remove some of them. And we're going to reduce it to just the major grid lines. Sometimes having references are helpful for direct comparisons, but sometimes too many grid lines can stray away from that helpfulness. So within the theme argument, we'll use panel.grid.minor. So that will be things that are in between tick marks on axes. And by specifying element blank, it will remove those. And element blank is really handy in general for a lot of the calls that will remove an element. So here we have a lot less cluttered background plot where we're just retaining grid lines for the major axes. So we can go a step further and increase the global text size, because a lot of the defaults in ggplot might not be the right size for if you have like a larger presentation that's needed, like for a PowerPoint or a poster. So I normally will define my sizes beforehand, because as was mentioned in the comment, that if you're making multiple plots, it's easier to use just a variable name than if you wanted to adjust the text size afterwards. So now in this resulting plot, we have the text size for everything. So axes labels, as well as the facet labels, all the same size. But to go a step further, we might want to make the facet labels slightly larger so they stand out. So we can also add an additional call in theme, and specifically addressing the strip.text.x. So that stripped this the facet text on the x-axis, and we'll just increase that to be larger than 15. So now we can see that that text is a lot bigger and stands out. But sometimes when you're increasing text size to make things more readable, we have our x-axis where a number of our labels are being overlapped. So one way to address that is to rotate them. So we can rotate. So within addressing our axis text on the x-axis, within that element text call, we are going to specify what angle we want our text to be, and then hjust specifying 1. And there's a lot of documentation online, but 1 will adjust so that the end of our words will come right under those tick marks. So here we have that adjustment where we can now more easily read the month and year on the x-axis, and they appear to be a lot clearer. So an additional adjustment, if we thought that maybe we wanted more space between our two panels, we can also adjust that with theme in terms of what we'll call is panel.spacing, and separating for this example just by 2 lines. And so that will look like this, where those plots might be slightly more separated now. And so the last adjustment that I have for this example is moving moving the legend. So currently the legend's on the right side, which is one of the defaults. But within theme, using legend.position, we can also specify top or bottom, or also the left. So sometimes the advantage when you have like a long time series, by moving your legend to the top or the bottom, it allows more space, so you can have a more spread out x-axis, so that things don't look quite as squished. And there's a lot of documentation on ggplots on their website in terms of all of the arguments, because there are a lot of things that we weren't able to show here today that can be adjusted. With that, I'll switch back to Allison for facets.
Thanks, Lauren. I am okay. Cool. Okay. So facets, as Lauren has mentioned, is a way to generate small groupings. So within the data, and it can be really helpful for doing direct comparisons, and you just have to keep in mind about why you're paneling and why you want to make these comparisons, or why you would want to group them together. So there are 3 different types of facets. There is null, wrap, and grid. Okay, this is grid, and this is wrap. So your grid will, create a grid, and it'll put in put it in as a, and then 1, and then this is just putting it together as just across. So you have to be careful about how you think about putting your data together when you create these facets. So this is an example of a facet within a published article, and you can see they have created cause of death and the variation across age, gender, and race. So you have your legend down here, and this is just a way to display a lot of information in a smaller graph, especially if you're limited. Again, you just want to be careful about how you're faceting things together. So the facet grid option is done by this little dot tilde option. So if you do it with dot tilde A, you get the spread that are vertically aligned, but if you put the name before, you get horizontal alignment. And I'll show you an example of this more specifically. But then you can also do the combination between them, which will do A is across the columns and B is down the rows. The wrap has a little bit more detail to how you want to how you can put it together. You can designate the number of columns and the number of rows to create the arrangement, and with the directionality as well. So one last thing is that there's also scales and facets. Yay, more scales. This is more ways that you can have control over the way that it's paneled, or whether it's fixed together. So meaning that it is fixed across the panels, your axes are. If you want them separate, as in you want everything on the X to be different, but everything on the Y needs to be fixed, you can do that with free X, and vice versa with Y. Or you can just say, I want everything on the axes to vary. And I'll show you an example of this going into. So as I mentioned, facets just generate small groupings within a subset of data. I'm going to go back to my hypertension example. So I'm going to create 2 individual plots here, one for males and one for females. And then I want to combine these. Let's say my data wasn't together in the first place, or it's just, I formatted it and I didn't want it that way. There's multiple reasons why. So let's just say that you want to do the males and females separately. So we have all of our graphing information of my two graphs, and then I have my colors. I removed my background. I don't want a legend because I am going to facet everything. So I'm going to remove that. And then I am just going to say that I want it faceted based on sex, and I want the scales to be free. So I'm just going to run this real quick. So I have my females and my males. So in this instance, I didn't necessarily need my legend, which we had talked about before about removing legends, because now it is fully labeled that this is my females and these are my males. And I just did, I wrapped it based on males and females here. So the next thing is that I'm going to show slightly different coding for the wrap. So in this instance, I just left it as sex and scales equals free here. Here I'm going to designate that I want one row in the horizontal. So I am just adding that into my facet wrap statement here. And I have an error. So all right, rather than make everybody sit here and watch me figure out why this isn't running today, because it ran this morning, I am just going to do the next one, and I will come back to that. So to create the grid, so before I was doing the wrap, and now I'm going to do the grid, I want to change my orientation, which is, this is the base that we saw before, and now I'm saying that I want to flip and create a horizontal grid instead of a vertical. So now it's just that instead of side by side, they're one on top of each other. And then going back to my other ozone example, I had ozone, I had NO2, I had a bunch of different other pollutants in there that we hadn't seen before in my air pollution data. So I am creating, it looks really like a lot more code than it is. So I am trying to create a facet for plots with the same scale of units for the concentrations. I'm going to create a label for my x-axis, and then I'm going to create labels for my y, and then I'm just going to create my plot, which we've seen before, of just putting in our specifications for our x and our y, how we want it grouped. I'm adding in confidence intervals for like your upper and lowers. Again, I'm adding in my labels here. And then creating a facet grid based on my pollutants. And I will run this. So I have then all of my pollutants faceted together, and it's year by concentration of ppm. And then we can kind of look to see if there are changing trends over time between, you know, ozone. We can see there's been a decrease, and we can kind of see this slow decrease in lead. And then you can also see over time, they all seem to decrease over time. So I can also switch the pollutant labels with the y-axis. And that's just simply saying that I want to switch here. I will run this real quick. It's a very similar plot. It's just slightly different. So before I had ozone over here, now I have it over here. My concentrations, everything is the same. It's just in different switching orders. So those are just a couple of ways that you can facet data together. And in this instance, we can look at the patterns over time between all of these pollutants of they're decreasing over time. They're in different colors for each pollutant. It's helpful to see that, you know, we have not only the point estimate, but we can also create confidence bands around them, and we can see differences over time. So this is why, you know, we could add in facets. There are multiple reasons to add them, but data like this kind of time series data is super helpful for determining patterns. So with that, I am going to stop sharing. Is there questions on what we just went over? Because if not, we will take another break, and then we will come back to mapping, which I know we already had a question about. So I think everybody's excited about that. If you do have a question, please drop it in the chat. Otherwise, we will see you in 10 minutes.
49, so it's been about 10 minutes since we started the break. Allison had a good point that noticing the chat for if people need to refer back to this PowerPoint presentation or also our R Markdown, we've placed that on our GitHub, and we have a link in the chat. So it might require you to scroll up a little bit depending on where it is, but Allison commented it out. But it's basically USEPA /data./viz/ggplot2. And we plan on further updating this with our current versions. What's up online right now is from a previous iteration of this workshop. So since I don't see any further questions, I'll go ahead and start section 3, which starts with mapping. Okay. So when location information is important to display, maps can be really useful. And there are a lot of resources in creating maps with R. For this workshop, I've really distilled it to a quick overview of mapping fundamentals that include layout and formats, as well as color palettes, and showing an example with continuous and categorical data using a chloropleth map, like this one to the right. So for spatial data types, there can be vectors, points, lines, or polygons, where lines are considered to be linear shapes that are not filled with any aspect, and that can include things like highways, streams, or roads. And I skipped over points, points which are specified to a specific location, and that's examples of that include cities or other landmarks. And lastly, there's polygons, which are closed shapes, such as county borders. There's also raster data, which is made up of pixels or gridded cells, and we've commonly seen this in terms of land cover. So before we can get to plotting, I feel a lot of time for creating maps is spent in data prep, and I recommend using the SF or spatial features package for loading and working with spatial data. An update last year made it far easier than other implementations to quickly go from loading data to creating a plot. SP is another common way, and it's a predecessor for SF. But when I was first learning R, I found that SP was a little tricky to get some external data attached to those spatial objects. But in general, the fundamentals are the same for the other plots that we've been working with so far in terms of loading, how to join or orient your data in the right specification, and then mapping it. With map layers, it's also important to consider the order for which you list your arguments. So if you want certain boundaries or spatial references to appear on top, their arguments need to be added later in the code. So showing here that if you want your cities to appear on top of these counties in North Carolina, they would appear a line under that other code. Map projections are also important. A projection is how information from a sphere is really plotted onto a flat surface. And features like size, shape, distance, or scale can be measured accurately on Earth. However, when we plot this on a flat surface, only some of the qualities can be accurately represented. So every map will have some sort of distortion, and the larger area that your map covers, the greater the distortion. And so it's important to decide beforehand what elements are important to the accuracy and what should be preserved. Typically for this bottom example showing the contiguous US, conic projections normally achieve less distortion at mid and high latitudes and are generally preferred for particularly the contiguous US. But there's a number of projections, and there's a lot of details in literature online that you can dig through to find the right one that applies to your study zone. So a lot of the other details I'll go through by going through this example. And so the data comes from a USDA, the Forest Service, and it includes county level counts of fires for 2 years. So we'll start by loading the shapefiles for state and county boundaries. Some packages, it's important to note, already have preloaded shapefiles for certain geographies. But for this example, we'll show how to load ones specifically if you've already created or have downloaded them directly already from census data or something similar. So adjustments we're going to focus on are adjusting the focus for map backgrounds, projections, how to add those in, color palettes, and then sort of the fine tuning in terms of line colors and thickness, and also showing an example with a facet. So I will switch back to RStudio. Okay. So for when I was first getting started with maps, getting the data prepped was the largest hurdle. So these first lines of codes were loading in our state and county shapefiles. So we'll run just this first part. And so we're also creating a data frame that has our year list for the 2 years that will be in our data set. So currently, if we were to put this, make the console a little bit larger. So just calling out one of the counties in the county's data frame, we can see that currently the county's data frame is set up where each county has a singular row. And that makes sense for the shape file that comes from the census. But for us to make our join that we have, since we have potentially 2 years of data for each county, we want to expand that so that counties now have 2 rows and an additional column that calls for those 2 years. So we're going to merge. And so the nice thing about SF is it makes it very easy to merge and sort of manipulate spatial objects. So now if we were to run for that first county again, we now have 2 rows, which is what we want. And that there's now a fire year column with those 2 years specified. So that'll make it easy to then merge in our data. So then once we load the data that we've downloaded, and just to show you what the top lines of that looks like, where for a county that has a singular FIPS, potentially could have 2 years, and then the 2 numeric values that we want to attach. So we're now working with apples to apples. This next lines of code we're going to left join, so putting the fire data on top of our counties. But it's important to note that in the US, there aren't fires in every county. So the original, what will get mapped where there's no data will have NAs. So the second line is just forcing all those NAs to be 0, because in this case, we know that an absence of data means that no observations were made. And just for the figure, looking at creating breaks so that we have a more categorical variable. And then since we're focusing on the contiguous US, this last part of code is just excluding Hawaii, Alaska, and Puerto Rico. So the default map, and for 2008, just focusing on that year to start, looks somewhat like this. And I will pull this. So we see the normal, what we would expect from ggplot, the rainbow default with our legend on the right side. So to add more focus to the map, we're going to minimize the background and also add a conic projection at the same time. And so we're going to add the conic projection by using chord.sf and using the CRS, and we can define that with the 5070, which is a conic projection, but there are a number of ones that could be used. And then theme void is the natural theme that removes all elements from a plot. So now we have our map that has the conic projection and already looks a lot more focused in terms of removing extraneous details. So some of the next things to think about are specifying the color palette that we want to use. So in this case, following and using a color palette from Color Brewer, using their orange to red. So sometimes red isn't always appropriate, but since this specific example is addressing fires, it might be more applicable and connect with readers. So here we've adjusted the color palette, and it's much easier to see compared to the rainbow one, that gradient moving from areas where there's less fires to more concentrated areas where there are more. But in looking at this legend, typically a lot of readers start top to bottom. So right now we have our 0 label at the top, and we might want to reverse that so that your eye naturally falls to the highest category first. So to make that adjustment in that same line where we're specifying the color, we're going to specifically use the guide argument and specify that within legend we're going to reverse, since the default is that normally it's not reversed. So now we have our figure where logically it makes more sense now that readers will easily see counties with, or what the color is for the max number of fires in a county could be. But in this figure, we can see sometimes with a lot of counties, especially in the US, it can get very cluttered with a lot of the lines, making some of the details harder to see. So we can make adjustments to the county line color, since we've also plotted state as well. And I think here I'll also point out, so in the main ggplot call, the initial data that we've attached to the main data set that's being called is the county data set. So this first geom.sf is specified to the county shape file. So we're changing that color using a hex color that's slightly lighter gray. And then this is where the layering comes in, where then on top of that, we're going to add this other geom.sf that specifies the states. And NA is filled as fill as NA so that they're empty, so that we're just going to have the outline of state be on top of the counties. So this adjustment will now look like this. So now we see that the counties are slightly lighter, so they kind of fall more into the background, but that the state shapes pop out more. So we can take this a step further and reduce the size of the county lines. So one of the challenges with maps, particularly US maps, is on the east, counties are very small, much smaller, so sometimes it's harder to discern, and they can appear more jumbled compared to western counties that have more area. So we'll specify the county line size to be 0.1, and we'll add that within the geom SF that specifies for counties. So the size of that line is now going to be 0.1. And in running this, I will say that visually within ggplot's graphics, you won't notice maybe the difference within how it's being portrayed. But as soon as you save this as a larger image or view it full scale, it would be more noticeable. So the last part is sort of combining everything together and removing that specification where we're only calling the year 2008 so that we can look at the facets since we've called 2 years. And to do that, you can still use that same facet grid that Allison introduced. And we're going to call that fire year variable. And then I'm just using switch so that my switch Y. So I'm moving that instead of having the labels for the years be on the right side, I want them to be on the left side, which is more of a personal preference. So now we have our 2 years with 2008 on top of 2009. And the advantage of using facets is that our scale now applies to both figures. So in some cases, you might have had a figure for 1 year and a figure for another year. But now we have a scale that does apply to both, which is nice. But we may want to go further and change the orientation of how the years are and also some of the text size. So again, you can specify text size. And so then again, through text, we're going to increase that to 15. And then specifying that using the strip text on the Y left, we want to make that angle 0 so that now this resulting plot has larger text in general, but that you wouldn't need to crane your head to look at how 2008 and 2009 are represented. So the second example I had looks at socioeconomic status. And the main parts of this, which I'll talk through while it's loading, is that we're just taking about 5 to 7 different characteristics from the census for these counties, and then running a factor analysis to create a scale that represents socioeconomic status. But for this example, I want to show groupings. So we then bin those into 5 groupings and then also into 10 groupings. And that'll become more apparent why I'm showing both. So this first snap is just the default map, and I've already added a projection and background that I find preferable. So in this example, purposely, I excluded some counties so you can see how NAs are handled. So when there's an NA, it's going to automatically assign it a color. But that might not. But we're able to adjust that color, and we also see ggplot's default rainbow background. So one option would be for the color palette to change it to a continuous one. So again, using color brewer, specifying the greens, and then in that same call that you can specify whatever NA value, what color value you want to assign to NAs. So for greens, this, as in other examples, we'll change it into a sequential scale for green. But for this, knowing that sometimes with factor analysis, there's not even breaks between the categories, that might not be preferable. Just showing this example with a discrete category using Color Brewer's Dark 2. Which is one of the qualitative ones, now has a separate color for each one. But this still might not apply to the specific case that well, since while it's not continuous in terms of that there's equal change between every group, we do know that it's ordered. So this is where the diverging palettes can be more useful. And I'm specifying in colors 5, calling out 5 colors to have specifically just the high and the low more prominent. So depending on what message you want your map to be, will really should drive your color choice. So since we're manually specifying colors, we'll use scale, fill, manual values to specify what colors, and then also in that call we can specify what NA color will be. So this is how that 5 grouping map would look like. So having lower SES with the category of 1, now more easily discernible from the highest SES group, 5. And for this example, which I've used before in maps I've created, the 2 through 4 were less important. So I personally made them a gradient of a color so that they were more similar, but not detracting from the 2 brighter colors that stand out more. The secondary example under this is just showing the default map using 10 groups. And it's pretty rare that you might have that many groups. It's sometimes really hard. The challenge with that is it's hard to discern sometimes the difference in color when there's so many groups, but sometimes that might be what is needed for your work. And I chose 10 just to point out that for greens in Color Brewer, but also many other palettes have a limited number of colors. So greens only has 9, so it's assigned up to 9, and then it won't assign anything higher than that. And you can make some adjustments around that. So using the color ramp palette, so telling them that we have 10 colors that we'd like, this color ramp palette is going to call, so you can put what color palette you want in there for greens. And then between the first and the last color that they have will equally divide up and create a color ramp to be able to be used. So just to show you what this looks like, because it also allows you to then pull out these colors for later use if you wanted to by hex code. So there we see 10 different hex codes. And then when we map this, we'll have now a color also for 10. So it is possible using that sort of hacky way to get more color options. Works better for the sequential palettes. It is possible for those categorical qualitative ones, but sometimes I've found that after a certain number, it's a lot of the end ones start looking more similar than you might want. So the last I had to share was switching back to the PowerPoint for maps. My cursor is. Yeah, was one of the examples that we found looking through the literature. This is from American Journal of Epidemiology, and highlighting this really as a great example of, while we didn't cover study site maps in this presentation, that we have a very clean picture of China and certain study sites that are being highlighted in their study. Their labels are very clear, nothing is overlapping. And this might be an area we might expand our workshop into in future iterations. But that what's really nice is that they use this sort of consistency between the rest of their figures in their paper. So this is just calling out another one of their figures where, you know, like the same point size is used. And it makes reading a paper much more easy, where you don't have to focus on reorienting yourself to how things are laid out, but having that consistent theme, I find really preferable. So with that, I think Allison might have the first example that we're running through. Okay.
Let me share my screen. Okay, so we are just going to go over a couple of examples of figures from the literature, and we're just pointing out maybe some enhancements that can be done to make them a little bit more easily readable and tell your story. So this first example is from an article from Epidemiology. It is a very simplistic figure, and it conveys what it needs to do, which is showing associations between hospital admissions to exposure, and from exposure to smoke wave days. So one thing about this figure is that the scales are on, for A and B are on two different scales. So on A, you see it goes from like a negative value up to +2, and then you see on B, it's like slightly below 0, and it goes up to 15. So when you facet these two figures together, it might be confusing because you're like, well, I can't really compare them when the scales are off. So just reorientating, like where is your y-axis, or whatever axis you're comparing on, and just trying to put it into a framework of, although they're showing cardiovascular disease in the right and respiratory disease in B, you may want to consider, when you facet together, what that means for your scales. So with that as being the big, I think here, okay, there we go. So this is just a little bit of an enhancement on how to kind of look at the data from, or the figure in a different way. So what I did, so we do have code for all these, and they will be on the GitHub site, but for the sake of time, we're going to kind of just go through these examples just through PowerPoint. So one of the things you'll see is that between the original example and this is that the gray background was removed. We increased the font size, we increased the size of the point estimates, we increased the width of the lines for the error bars, and then we created a facet in which they're on the same scale. So just a little bit, this was what it looked like before and what it looks like after. So it makes the comparison a little bit easier when you can see things on the same scale. And then we also try to remove out some of the extraneous details that might maybe inhibit a little bit of the readability, or just tell your story, because this just helps to streamline it and make it a little bit cleaner. So then the next example we have is an article, and this is going to be displaying trend lines with confidence bands. So as you can see here, we have year across the X and different treatments, differences between the treatments and controls for the time period. And you're supposed to have this orientation mark. It says 2005 is the reference category, and it's slightly a little bit off on this one, where your reference is. And then the confidence intervals being in red as well as the reference line is a little bit too close together. So one enhancement that can be done with this is to create, we can create 2 reference points, one for 2005 and then your 0 as well. And then what we can do is create the bands for them. So we can change the color, and then we can create a band for the entire trend over time. Another way to do this would to be change the way that the confidence band is done. So here we did different kinds of lines, so and in a different color. So it's the same figure, it's just slightly different, and we kept within the same color palette for the confidence band, because before you saw it in red with the references also in red. So it's like this way you know that, oh, it is part of the same color palette and it is in the same pattern as well. It's just with the point estimates, it's just a little bit cleaner and a little bit more streamlined to not be so alarming that is there more than one thing on this figure. So those are just a couple of enhancements that can just be done to just kind of streamline and make it a little bit cleaner, a little bit neater. And I think Lauren, you have the next one?
I do.
Okay, I will stop sharing.
Okay, so for this example, let me pull it up to full screen. So this example has long-term PM exposure and looking at different risks for different diseases. And the challenge, and we've seen a lot of figures like this, is the challenge is fitting multiple plots in one figure and having a common legend. And one of the difficulties with this current figure is that the main key is only an A. So it's sometimes preferable to put it in a more neutral position so that it's more easily identifiable that it applies to all of the plots. So for making slight adjustments, in that other one, we have moved the legend position to be more to the right. And so it might be more intuitive that it applies to all of them. But then also, sometimes when it comes to so in this example, they have moving averages, which are their grouping variable by specific cause. So they have 5 different things grouped within each category on the x-axis. And originally they had chosen the size of a shape to show the differences between those categories. But another route might have been to use different shapes in general to make that more apparent. Because in the first figure, especially depending on what size a journal might print it at, some of those other estimates appeared pretty small. And the downside sometimes of using size is that I think we naturally assign more importance to larger things. So your eye will naturally get drawn to like their largest points, whether that's what they intended or not. So we can also increase axis labels and then also alter the background some. What's this? So in this slightly altered version, minimizing, so the last version had ggplot's defaults going through 5 different shape sizes. And this one you can specify shapes. So in this case, going from 2 different circles to 2 different triangles and to a 3rd triangle. So by using the same shape, 3 shapes, but then having alternating color patterns is sometimes a way if you have like a number, because 5 can be a large number of shapes to show distinct differences depending on, like how big this figure will be printed. But this shows shape, which looks a little bit cleaner, is easier to see, and now there's sort of equal importance kind of assigned to each one of those inner groupings. And then I believe Alex has example 4, so I can switch back.
Okay, thanks, Lauren. Yeah, so this is an example that we pulled since it kind of dives into facets, which we've been talking a lot about, and also color scheme. So those are the 2 main points that we kind of want to talk about with this figure. So this is for looking at age-adjusted mortality in the US over a 15-year span. And it's looking at this based on sex and race ethnicity. So on the left-hand side, we have looking at male and female as well as total. And on the right-hand side, we have different race ethnicity for 3 different health outcomes. So something that kind of jumped out at me for this figure that we could perhaps modify is something that's come up a lot in this talk, is that we're using a rainbow gradient, which can make it a little difficult to distinguish between colors, especially in this case. There are a lot of colors on the plot. There's also colors that may not necessarily be colorblind friendly. And so, it's something that we want to maybe improve upon a little. There's also a lot of lines in each plot, so it makes it a little difficult to read, the figure lines as well as the background lines. So, looking at whether or not those lines are actually helping or hurting to convey the data. Another thing that makes this plot a little on the busy side is the fact that each of these figures share the same x-axis. They're all going from 2000 to 2015, but we're seeing that repeated for each of the 6 plots. So that does make it seem a little busy. Okay, so addressing each of those things. In this version, we've used facet for the disease type, and we're doing separate panels for sex and race ethnicity. So that takes care of that last issue of repeating year on the x-axis for everyone, and sort of cleans up cleans up the figure a little bit and makes it easier to just kind of go straight to the data. We also, with this one, chose a different theme that has lighter background lines. We kept the background lines in this case. It does sort of help orient you to the values on the y and x axis, but lighten those up a little bit. We also used unique colors for the left and the right panel. So we don't have any repeating colors here. We did pull these from the same palette. So as Lauren and Allison went through, how to kind of create your own palette and manipulate which colors you're pulling where, this is a case of that, where we're using the same palette. But splitting the colors up across each panel. We also made sure to pick a palette that was colorblind friendly. So that helps make things a little bit clearer. And another trick, and this was actually something that I learned in graduate school. My graduate school advisor always recommended that you order your legend variables in the same way that the data appear in the chart. And sometimes that's not always easy to do, but in this case, it actually does help, where when you're reading the legend and you see the first one is male and then total and then female, and you come down to the plots and you see the same pattern, and it makes it a little bit easier to read. So that was something else that we did. So this is pretty good. It's a little bit less busy than we had in the first place, conveys the same information. If you wanted to go a step further, one other way we could do this is to actually use shapes for one variable and colors for another, to further draw your attention to the fact that on the left, we're looking at males and females, and on the right, we're looking at those ethnicity. That would be one other thing that you could potentially do. So, okay, I think I'm going to pass it back to either Lauren or Allison for example 5.
Yeah, I have example 5. I'll start sharing. So in this example has the continental US map, and they have two colors that they've pointed out in terms of attainment and non-attainment counties in the US. And things that point out to me first are map projection, and then whether this graph could or figure could be enhanced by adding a legend. So potential changes, so using similar data to the originally presented graph, we have changed the projection to that more conic shape, and then have added a label or added a key for the colors as well. They did have in their figure from their manuscript the description of what the colors represented. I sometimes find, even though it's somewhat redundant, to still put that in there if there's space and it doesn't sort of detract from the overall map. Because when you're flipping through, it's sometimes easy to see in more visual, if you're a visual learner, to make that connection faster. So for example 6, which is sort of a similar vein, talks to map boundaries. So in this article, they're showing a map of the US with counties with different color variations based off of life expectancy. And the challenge of this, counties in the US and probably other areas where there's some with very tiny shapes, it gets hard in some of those eastern counties to tell, is it just a densely packed county in terms of lines, or like, is it one of those lighter shades of colors? So first mapping that to sort of similar to how that original figure was, having all the boundaries the same size, and the map sort of looks like this. But then making that adjustment by here, that line size difference can be seen more between counties having smaller lines that are gray and retaining larger, thicker state lines, which might make those eastern counties, their fill up more space to allow them to be more easily observed. And then the last example uses map colors and labels. And it shows one of the challenges in displaying multiple pieces of information on one map. So here they have both smoke wave days per year as their color gradient, but then they're also displaying counties with high population in that sort of hashed mark to fill in a county. And that can be really complicated because it's adding a layer on top of another layer, which especially depending on like how close together some hash lines are or what that shape is you're adding on top, could make that county's underlying color look a little bit darker or muddle it completely. So first showing sort of that base map, where one suggestion I would have, and just to float back to that other one, their original one also had state labels. And depending on your presentation, like particularly maybe you're working with state partners, labels might be very important. But for larger presentations, specific areas might be more intuitive depending on your audience. So you could remove your state labels and then create that sort of smaller county boundaries so that they stand out more. So just creating less things in the way of seeing what colors you're trying to show. And then another suggestion might be that displaying populous cities in this case, instead of adding another sort of shape fill on top of a map, is another way to go about stressing a different type of point. So in this case, just adding points for cities that are larger than 100,000 in population might be a way to both co-show where a large number of smoke days occur and where a large part of the population might be as well. So we've also included references, but this comes to sort of the end of our prepared slides. I'd have to pull up the chat to see if there's any questions there, but we can also open it up to see if anyone also has burning questions they'd like to share or other tips that they use in their work.
There's nothing in the chat right now, Lauren.
Okay. Well, one thing is we definitely really appreciate everyone sticking with us. It's been a long workshop for over 2.5 hours. So we really appreciate the time of you guys sitting in with us. And do want to point out that, our materials are going to be on our GitHub, and it also has our contact info. So if you have follow-up questions, feel free to contact us.
A question just came in. Boundary outline size is defaulted 0.5. What might be the problem when the size function doesn't work for the value smaller than 0.5?
Yeah, so in specifically addressing maps, a lot of times, and this gets to the viewer that ggplot or that your base, whatever viewer you're using might have, is that you might not visually see that difference below 0.5. Because at least for lines for some shape files, you can get down to 0.1. I don't think I've tried ones that are less than 0.1, but that until you enhance it on a larger scale and save it as a larger image, that it just might not be visually distinct on the way that you're viewing it if you're viewing it in RStudio.
Well, we can give everybody 19 minutes back of time. But if you have questions, please don't hesitate to reach out to us. There's information for will be on the GitHub, and we just want to thank everybody for attending today.
Yeah, and we can, I at least can stay on the chat for a little while longer if folks have Questions? Okay. Yeah, thanks everyone for coming.